If LDL is the bad cholesterol, why does your liver spend all day making it? That doesn't make much sense, does it? Today I'm going to show you why LDL isn't really the villain most people think it is, and why another particle that hardly anyone talks about deserves much more attention. Let's imagine a survey carried out right now. Let me ask you, what would you say if I said, tell me what LDL cholesterol is? Almost every one of you would probably give the same answer. It's the bad cholesterol. And if I asked about HDL, well, that's the good cholesterol. We've been hearing those phrases for decades. They're so familiar that most of us have stopped questioning them. But here's the problem. Neither LDL nor HDL is actually cholesterol. They're delivery vehicles. And once you understand what they're delivering, where they've come from and why they're there in the first place, the whole cholesterol story starts to look very different. In fact, by the end of this video, I think that you'll realise that whether LDL is good or bad is rather like asking whether a delivery van is good or bad. It depends entirely on what's inside it, how many are on the road, and why there are so many of them. Hello, my name is David Van Dyke, and welcome to or back to this channel. On this channel, I try to cut through the myths and simplify the science so you can become an expert in your own body. And if that sounds like something you're interested in, then please do subscribe. Today we're going beyond the labels of good and bad cholesterol to discover what's really happening inside your bloodstream. And very quickly, I've heavily researched this video to make sure of its accuracy, as it's such an important subject. So I've linked the key scientific papers discussed in this video in the description below, so you can read the evidence for yourself. Let's start at the beginning now. Every cell in your body needs fat. Your brain is around 60% fat by dry weight. Every cell membrane is built from lipids, and cholesterol is used to make hormones like testosterone, estrogen, and cortisol. It's also needed to produce vitamin D and bile acids that help digest food. Without cholesterol, life simply would not exist. And this isn't controversial, it's basic human physiology and is described in every major medical physiology textbook, including Guyton and Hall's textbook of medical physiology and molecular biology of the cell by Alberts and colleagues. Cholesterol isn't something your body reluctantly tolerates, it's something your body cannot survive without. So the question isn't why your body has cholesterol, the question is how it transports it. And here's the problem. Imagine pouring cooking oil into a glass of water. The oil floats on top because fat and water don't mix. Your bloodstream is mostly water. So if your liver simply released fat into the blood, it would clump together into large oily droplets that couldn't be transported efficiently around the body. Nature solved this problem rather elegantly. Instead of releasing naked fat, the liver wraps fats and cholesterol inside tiny protein-coated transport particles called lipoproteins. You can think of them as microscopic delivery trucks. Different trucks carry different loads, and that's where names like VLDL, LDL, and HDL come from. They're not different kinds of cholesterol, they're different transport systems. The transport system has been understood for decades and forms the basis of everything we know about lipid metabolism. One of the classic reviews by Richard Havel described lipoproteins as the body's solution to transporting water-insoluble fats through an aqueous bloodstream. So let's begin with the truck that almost nobody talks about, VLDL, very low-density lipoproteins. Your liver manufactures VLDL particles primarily to transport triglycerides, the body's main storage form of fat, from the liver to tissues that either need energy or want to store fat for later. Although VLDL also contains cholesterol, triglycerides are its main cargo. A comprehensive review published in the European Heart Journal in 2020 by Jan Boren and an international panel of lipid researchers describes VLDL as the liver's principal transporter of endogenous triglycerides. This isn't an alternative theory, it's established physiology. And this is important because triglycerides tell us a great deal about what's happening metabolically. When triglycerides are consistently elevated, it often suggests that the liver is converting excess energy, particularly excess refined carbohydrate and sugar in susceptible individuals, into fat through a process called de novo lipogenesis. These newly made triglycerides have to leave the liver somehow, so the liver builds more VLDL particles. And this is why elevated triglycerides often accompany insulin resistance and metabolic syndrome, not because triglycerides are the original problem, but because they're a visible sign that the liver is working overtime, processing excess energy. One of the scientists who has spent decades studying this is Professor Elizabeth Parks from the University of Missouri. Her work has shown that when excess carbohydrate is consumed, particularly in insulin-resistant individuals, the liver converts more of that carbohydrate into fat through a process called de novo lipogenesis. Those newly made triglycerides are then packaged into VLDL particles for transport around the body. This also explains why your triglyceride blood tests can tell you much more than simply how much fat is circulating in your blood. Most of the fat stored throughout your body, including visceral fat around your abdominal organs, is made up of triglycerides. So persistently elevated triglycerides often go hand in hand with increased visceral fat and worsening insulin resistance. It's one of the reasons doctors pay close attention to them. In fact, elevated triglycerides are now recognised as one of the hallmarks of metabolic syndrome, a condition closely linked with insulin resistance, fatty liver disease, and increased cardiovascular risk. So what happens to a VLDL particle after it leaves the liver? Imagine one of those delivery trucks setting off fully loaded. As it travels through the bloodstream, enzymes gradually unload its triglycerides, delivering them to muscle tissue for energy or to fat cells for storage. As more triglycerides are unloaded, the particle becomes smaller and denser. Just think of the truck unloading and therefore becoming smaller. Eventually it becomes an intermediate density lipoprotein, or IDL. Then more triglycerides are removed. The particle shrinks again. Eventually what's left is LDL. This entire pathway, VLDL becoming IDL and finally LDL, is described in virtually every lipid metabolism textbook and was summarised again in the 2020 European Heart Journal consensus paper. LDL wasn't created to cause disease. It's simply what's left after a VLDL particle has finished much of its delivery journey. Even LDL still performs important jobs, carrying cholesterol that cells throughout the body require for normal function. Your liver makes LDL because your body needs it. So why has LDL earned such a bad reputation? Part of the answer is that not all LDL particles are identical. Some LDL particles are relatively large and buoyant. Others are much smaller and denser. Much of what we know about these particles comes from the pioneering work of Professor Ronald Krauss at the University of California. His research helped establish that LDL isn't one uniform particle, but a family of particles that differ in both size and density. These are known as small, dense LDL particles. Research has consistently shown that people with a predominance of small, dense LDL tend to have a higher risk of cardiovascular disease than those whose LDL particles are mainly larger and more buoyant. One proposed explanation is that the smaller particles may penetrate the arterial wall more readily, are more susceptible to oxidative modification, and often occur alongside insulin resistance, elevated triglycerides, and low HDL. But there's an important point: small dense LDL rarely appears in isolation. It's usually part of a wider pattern of metabolic dysfunction: high triglycerides, insulin resistance, excess visceral fat, low HDL, elevated ApoB particle numbers. These often travel together. So where do these small dense LDL particles come from? One of the biggest contributors appears to be insulin resistance. When our muscle and liver cells respond poorly to insulin, glucose remains in the bloodstream for longer after meals. The liver responds by converting some of this excess carbohydrate into fatty acids. Those fatty acids are assembled into triglycerides, and the triglycerides are packaged into VLDL particles. More VLDL production means more particles, eventually being converted into LDL. Under these conditions, a greater proportion of LDL particles become the smaller, denser variety associated with higher cardiovascular risk. Numerous studies have found that people with a predominance of small, dense LDL particles are at a greater cardiovascular risk. Ronald Krauss' work first brought widespread attention to this phenomenon, and subsequent reviews published by the European Atherosclerosis Society have confirmed that small dense LDL is more likely to penetrate the arterial wall, remain in circulation for longer, and undergo oxidative modification. The story begins long before cholesterol enters the picture. Researchers now recognise that insulin resistance changes the way the liver handles nutrients. Rather than efficiently storing glucose in muscle and liver glycogen, more carbohydrate is converted into triglycerides, driving increased VLDL production. This relationship has been demonstrated repeatedly over the past 2 decades. It begins with metabolic health. For years, we focused almost entirely on LDL cholesterol, but many researchers now believe a different measurement may tell us even more: ApoB. If you asked many preventative cardiologists which single blood test they would choose if they could only have one, an increasing number would say ApoB. Every VLDL particle contains one ApoB molecule. Every IDL particle contains one ApoB molecule. And every LDL particle contains one ApoB molecule. That means an ApoB blood test effectively counts the number of potentially atherogenic lipoprotein particles circulating in your bloodstream. Imagine 2 people who have exactly the same LDL cholesterol result. One person could have relatively few large LDL particles. The other could have many more small particles carrying the same total amount of cholesterol. Their LDL cholesterol result would look identical. Their particle numbers could be very different. In 2024, the National Lipid Association published an expert clinical consensus stating that ApoB more accurately reflects the total number of atherogenic lipoprotein particles than LDL cholesterol alone, particularly in people with obesity, diabetes, or metabolic syndrome. That's why many lipid specialists increasingly regard ApoB as one of the best single markers of cardiovascular risk, particularly in people with insulin resistance, obesity, or metabolic syndrome. Okay, so where does HDL fit into all of this? Now, HDL is often, as we know, called the good cholesterol, but once again, that's an oversimplification. HDL particles help transport excess cholesterol away from tissues and back towards the liver, where it can be recycled or eliminated, a process known as reverse cholesterol transport. That's undoubtedly an important role. However, simply having a high HDL cholesterol level doesn't automatically guarantee protection from heart disease. Researchers increasingly recognise that HDL function, how well those particles perform their jobs, may matter just as much as the amount measured on a standard blood test. So HDL simply isn't good. Scientists have spent decades trying to raise HDL cholesterol using medication, and surprisingly, despite successfully increasing HDL levels, many of those drugs fail to reduce heart attacks. This led researchers to rethink HDL entirely. Today, many believe that how well HDL functions may be more important than simply how much HDL is present. It's another transport system carrying out a different task. The picture that emerges is far more interesting than the one most of us thought. Cholesterol itself isn't the villain. Your body manufactures it every day because it's essential for life. The real questions are these. Why is your liver producing so many triglycerides? Why are there so many VLDL particles being made? Are you developing insulin resistance? Is your triglyceride level rising? What's happening to your ApoB particle count? And are those particles becoming predominantly small and dense? These questions shift the conversation away from simply blaming cholesterol and towards understanding metabolic health as a whole. If there's one message I'd like you to take away from this video, it's this. Stop thinking in terms of good and bad cholesterol. Start thinking about healthy metabolism. Interestingly, this shift in thinking is reflected in recent European and American lipid guidelines, which increasingly emphasize ApoB, triglycerides, and overall metabolic health alongside traditional cholesterol measurements. Because when we improve insulin sensitivity, reduce excess visceral fat, become more physically active, eat minimally processed foods rich in fibre and appropriate amounts of healthy fats, and keep triglycerides under control, we influence the entire lipoprotein system, not just one cholesterol number on a blood test. Cholesterol was never the enemy. See you next time.